If you remember, Netflix at the time shipped DVDs. And streaming was a tiny workload that had just launched around the time I joined. We broke it multiple times. And there's this idea that you want to be a small fish in a large pond. Whichever cloud you're using, there's a program you can use to share data that's, I think, very relevant to the HPC community.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hey Shaheen, great to be with you again. I understand we have a special guest this week.
We sure do. Our special guest is Adrian Cockcroft, one of the real rock stars of cloud computing. Adrian and I worked at Sun Microsystems together when we were part of the HPC team, and he was the CTO, chief architect for that group. Prior to that, he was a distinguished engineer at Sun, focused on performance and capacity planning, and wrote the definitive book on that topic, which continues to sell, and you see it on bookshelves. Then from Sun, he went to eBay, a lot of focus on big-time horizontal scaling and a precursor to extreme scale, hyperscale that we'll get to in a second. And at Sun, we were also pushing grid computing, if you remember at that time. Then from eBay to Netflix, 7 years there, and one of the key architects to move Netflix to AWS, and we want to ask him about that. Then to the venture capital world for 2 or 3 years. He was a keynote speaker at our Startup HPC conference back in New Orleans in 2014. Thank you for that. And then from there to AWS for 5-6 years there. And now from about a month ago, we are delighted that he joined Orion X to focus on consulting and advisory. So Adrian, thank you. Thank you for making time.
Thanks. It's great to be back working with you again. We had a lot of fun in 2003, 2004. I learned a lot then when we were doing HPC, and then unfortunately Sun was shrinking, and we all had to kind of move on and find something else to do for a while. So
That's right.
it was good to come back and work with you again, Shaheen.
Indeed. So let me ask you first about Netflix, because when Netflix went to AWS, it was relatively early days of cloud, and it was a big deal. It really got a lot of attention as, oh my God, big companies who are really relying on their IT infrastructure the way Netflix was so dependent on it are making this move. And of course, in retrospect, it was a great opportunity for all involved. So tell us a little bit about how it all went down and the challenges and the joys of it.
Yeah, there was a long story there, but one of the things was we knew we needed to scale for streaming, and we were currently set up to scale for DVD. If you remember, Netflix at the time shipped DVDs. And streaming was a tiny workload that had just launched around the time I joined. But the growth rate of that workload was so high because we were converting existing customers to streaming, and the amount of back-end compute you need to support a streaming customer is vastly higher. It's like 1,000 times more than a DVD customer. Right. However, it costs a tiny fraction of shipping a DVD in the mail back and forth. So it was cost us less to serve a streaming customer, but they used a lot more resources. So we had to suddenly scale our entire data center infrastructure extremely rapidly because we weren't doing customer acquisition. We were converting our existing customer base of roughly 10 million customers at the time. Netflix is now, 150 million or something, 200 million? I think it's 200-ish. So and we wanted to build something that would scale to the 50, 100 million plus sort of thing. So an AWS sounded plausible, and we talked to them, and they said, in 2008, and they said, come back next year. We're not quite ready to deal with what you're talking about here. And we came back the following year, and they said, okay, let's see if we can make this work. And we'd started putting some of the more not customer-facing workloads, like encoding. There's a lot of video encoding. It's a really big, heavyweight workload. Thousands of machines at the time were used for it. But I remember one time we went, let's make an API call and ask for we had an autoscaler. What happens if we set it to 3,000? Is that going to work? We said, I don't know. Let's go find out. So we just set it to 3,000, and the limit had been set high enough, and 3,000 machines appeared about 40 minutes later, and we went, well, that's cool. That's that. Don't try that at home by talking to your ops department. And then we said, well, how about if we have some machines somewhere else in the world? So we fired up some machines in Brazil at one point with no people in Brazil. So it was this sort of realization that we could ask for compute on a larger scale without having to wait and anywhere in the world was what we needed to support Netflix as it rolled out globally. And that kind of continued, and we ended up growing pretty rapidly into that and really pushing. And then the other part of it was a very strong partnership with AWS, where Netflix said, "Okay, you need to fix this aspect of it. We need a way to solve this problem." And AWS was listening and building what we needed, and there were a bunch of other people sort of slipstreaming Netflix and using those capabilities. So Netflix was sort of like you see startups, they typically have 2 or 3 customers that drive what that startup's functionality is. We were one of those customers for AWS, basically, but at a much bigger scale.
So it was a kind of an initial, very rigorous test case for AWS, you could say.
Yeah, we broke it multiple times, and there's this idea that you want to be a small fish in a large pond in the cloud. You want the cloud to be very big, and you want to be very small, right?
Yep.
If you're a shark in a paddling pool, it doesn't work. You're longer than the paddling. You don't fit. And for a long time, like the Google Cloud people turned up and said, "Hey, why don't you run in Google Cloud?" Say, "Well, how big are you?" And they said, "No, you're not big enough. You have to be this tall to ride this ride," kind of problem, right? Google didn't actually have enough capacity to run Netflix because Netflix was bigger than that already. And so there were a number of things. Now, of course, so part of the strategy of going out and talking a lot about what Netflix was doing was we wanted to encourage more people, more fish to come into the pond so the pond would get bigger faster than we grew, if you see what I mean. The analogy gets a bit stretched, but it was important to us that AWS succeed because we wanted it to feel like an elastic resource that we could just ask for something, it would be there, and we didn't want to keep hitting the limits. And nowadays, any one customer, I mean, you can go find a small region somewhere and you can find a limit, but in the major regions, it's pretty hard to hit the limits, even if you're very large.
Well, I know as of, I want to say 2015, at that point, Netflix was consumed a healthy proportion of total internet traffic
Yep.
on a given day or a given week.
hmm
Amazing.
Yeah, it was actually before that. What happened was Netflix was very much under the radar for a long time. And internally, somebody went to talk to Google about something and came back and they'd managed to find out Google were boasting how big YouTube was to them. And they came back and said, "We're doing more bandwidth than YouTube." No, well, no, we can't be. Well, we're doing many fewer transactions because we were doing hour-long videos at high resolution, and YouTube was doing 30-second videos at low resolution. But the actual bit rate of Netflix passed YouTube very early on, and we were just going, "Wow, okay, I guess we need to keep building this CDN capability." And then Sandvine is a equipment supplier that started publishing reports, and they just listed Netflix as 20 to 30% of the entire bandwidth going into homes.
Yeah.
And people were going, "That can't be right," and whatever. And they said, "Yeah, that's about right." And that was when the sort of cat was out of the bag, and everyone started realizing that Netflix wasn't. For a long time, they thought Netflix was failing and going to fail, and everyone else was going to take them out. And they just got very big very quickly and managed to do an end run around all the competition.
By the way, it occurred to me the old Netflix model way back in the day of sending DVDs. You could say that's an example of very large bandwidth, but
hmm
really bad latency, right?
Yeah, the
Yeah.
SneakerNet
Yeah, exactly.
thing.
So
Yeah, a truck full of tapes traveling down the highway was
there we are.
the
Exactly.
old quote. Yeah.
Yeah. Well, let's go further into your career at AWS. I guess one of the projects you were very focused on was sustainability.
Yeah, so I started off working on open source, and then for the last year or so at Amazon, I was working on sustainability. And I started managing a program that had been running for a few years and was a little bit unloved and needed some help and support. And so I took over. I got Anna Pinheiro-Pinette, who's been running it for a long time. She's a PhD climate scientist, was previously in the White House in the Obama administration as their climate data czar. And she'd ended up getting hired into AWS to build a climate data repository on AWS. and it was a sort of just bouncing around from one manager to another over the years. And so I said, okay, let's see if we can do something with this. So I transferred her to work for me, and we focused a bit more on making this a more successful program. And actually, before I left Amazon, we transferred it into the HPC organization at AWS. So there's an HPC go-to-market organization, and she now reports up into that group. So it's all tied into that space. But the initiative, there's two levels of the initiative. There's an open data program, which has been running for many years on AWS, where if you have a data set you want to share, then you can go to AWS and they will zero out the cost of sharing it. But sitting on top of that, we had the Amazon Sustainability Data Initiative. That's this program that Anna wrote, has been running for years. It was launched in 2018. But I don't think it's well understood. And there are many large data sets, which, particularly in the HPC space and in the climate space, where the data is public. You've got Sentinel data for satellites. You've got the extreme weather database that the UK Met Office runs. These data sets are public data, and those data sets are shared on AWS. So if you're a customer of AWS, you get an S3 bucket, you put your data in it, you apply to the program, and AWS zeroes out the cost of that S3 bucket to you. And there's something like 100 petabytes of data in this program. So you can go for a really large data set. So you can be tens of petabytes if you happen to be at that scale, which is expensive. And you can basically say, I want to share this with the world. I'm going to have it on Amazon and anyone can use it. And then the cost to the UK Met Office or NASA or NOAA, whoever owns these data sets, is reduced because AWS is basically zeroing out the cost of that bucket in your bill every month. And then on top of that, there's a grant program where you can get AWS credits or even funding for teams to go and do something with that data, or in the process of building some of that data, creating some of that data. So Anna has been running this program for a while. There's several large projects that have been done there. One of the big ones most recently was NCAR and an NGO called Silver Lining took NCAR's global climate model and moved all the data to AWS. And that work started last year. I think it's finishing up around now, to have everything you need to run the entire global climate model and a 30-year run of the entire world, and have all of the input and output data and all the code and everything sitting there ready to run on AWS. So if you want to rerun it, you can go find this data set, and all you have to do is bring compute. The data's already there. And also the users of the data don't get charged for accessing the data, even if they're outside the cloud. It's just a really efficient way of managing large amounts of data. And I should say that there's a similar program on Microsoft called Planetary Computer, and a fairly similar program, although different in some ways, on Google called Google Earth Engine. It's a bit more AI focused on the Google side. So that, whichever cloud you're using, there's a program you can use to share data that's, I think, very relevant to the HPC community.
Very much. It's also a good way to really preserve and safeguard the data as well, because you now have that discipline around it, and excellent.
Yeah, you have to there's a contract that says I own this data and I promise to keep it up to date. That's basically it, and then they'll just credit your bill. And it's it's in the sort of a bit of the goodness of your heart thing from Amazon, but it encourages workloads to move to the cloud. That's sort of the business justification for it. But it's also part of a Tech for Good program that particularly the public sector organization has a lot of support for charitable and nonprofit organizations, where they do a lot of zeroed out funding and kind of deals for nonprofits.
And they have other similar programs in other fields. What are some of those other projects?
Yeah, so there's also a lot of, through COVID, there was a large amount of COVID-related healthcare and gene sequencing and all of that kind of data. There's a massive data set there. There's government data, government statistics. There's astronomy data. Basically, any large data set, particularly public sector data sets around the world, many of them have been put on the Amazon Sustainability Data Initiative. If you want to go find it, it's amazonsdi.com. That's the easiest way of getting to it.
Brilliant.
Okay.
Now, you mentioned 100 petabytes. Compared to all of S3, this is still a small fraction.
Yeah. It's a small enough tax that as long as it doesn't get to be too many exabytes, we're good.
Right.
Right. So they're comfortable with it being a free funded resource at the 100 petabyte level. And that's kind of the S3 team effectively subsidizes the program that way. There's lots and lots of exabytes going on at AWS.
Yes, I imagine. Well, so let's move to HPC and cloud. That's been an area that's been growing. We covered it several months ago. Let's talk a little bit about that, what your experience is like and how you see it work or not work, etc.
Yeah, I had actually a fairly hands-on experience. I was involved in the Formula One motor racing deal that AWS put together a few years ago. I was actually helped connect some of the dots, and I was involved, and I went to some races and things like that. But part of that deal was an aerodynamic simulation of the next generation cars, which are the current cars. This is the first year they're running these cars. So 2 or 3 years ago, they simulated the car. So this is using CFD, and it's using some software called OpenFOAM, which is a CFD simulation package. And they didn't want to just simulate the aerodynamics of one car. They wanted to have a second car in the wake of the first car. So you've got a car and there's another car behind it, and then they need to simulate at different distances and offsets and going around different kinds of corners at different kinds of speeds. So if you're simulating aerodynamics on a single body, okay, you have all these permutations, but it's constrained. When you add the two bodies with all these other things, it's basically they had a permutational explosion, right? The amount of compute they needed and the number of combinations they needed to do was just ridiculously beyond what they had. And they had a small dedicated cluster, little InfiniBand cluster, like I think it was like 500 nodes or something like that. 500 cores, something like that, that they were running the work on, but they needed vastly more. So when they joined the AWS program, we basically figured out, okay, what we need to do is get this workload running on AWS, scale it up, and let them run lots and lots and lots of these jobs. And then once they finish simulating this next generation car, they actually don't need it anymore, and they can drop back to just a really small footprint. So they had just a big chunk of work to go through. And that was sort of an ideal cloud environment. I need an enormous amount of capacity for a limited amount of time is perfect for cloud. So we ended up with, I think, a 2,500 core was the largest cluster. It was running in 2 days. I think they got it down to about 6 hours on the bigger cluster. And it was a little less efficient. And this is because the AWS clusters, I mean, we tuned up, we had to get all the latest versions of MPI and everything in there. The AWS, you're running on a fabric adapter on an Ethernet based network. And it is highly optimized and low latency, but it still gives you some scalability limit. So it's sort of tens of microseconds latency on the EFA. Whereas if you're running on InfiniBand, like the data center thing they already had was sort of single digit microseconds roughly for InfiniBand. I'm ballparking here, but the AWS optimized Ethernet is probably an order of magnitude faster than just running it over standard Ethernet, but it's not as fast as a dedicated HPC oriented network. So there's sort of a limit to your scalability and what you can do. So we kind of learned a little bit about those limits and tuning as much as we could to get the workload to scale. And then, the next generation cars came out. Everyone did their work to come up with the new cars. And this year, the Formula One cars, there's a lot of variety in the design because they all had new rules and some are working better than others. And it's actually been a fascinating season to see the effect of simulating a car. And the idea was that you wanted a car to be able to follow another car around a corner without having its aerodynamics, its downforce, losing too much downforce. And that seems to have worked out. So overall, an interesting project and a lot of scalability work. But I think that's kind of the sweet spot for running on the cloud is where you want a very large amount of capacity for a limited amount of time.
The issue around InfiniBand Ethernet, we know Azure has InfiniBand. Mm-hmm. Is this I've always wondered why doesn't AWS incorporate InfiniBand as well?
I think some of it is just sort of philosophical difference. They've just been tuning the fabric adapter over the years to say, well, this is good on most of the workloads, but there are certainly cases where the latency gets you. There are other problems at scale. If AWS announces something, customers will flood in and start using it. So you have to be ready to run at scale. So when they announce a new instance type, an high performance computing oriented instance type, they have to have volume. Otherwise, everyone comes in and it's not there because the customer demand is so high. The other thing is AI is a big workload. So we've got the GPU-based workloads and the machine learning training workload, which is driving a lot of the large-scale GPU-based instances, is not really latency sensitive. It is bandwidth sensitive. So they're running 400 gigabit and most recently 800 gigabit from a single instance. You can get an AWS instance full of GPUs with 8 100 gigabit lanes coming out of it. And that's really so it can pump all of the data in and out for these very large training jobs. But I think the workload there is a little different to, say, OpenFOAM, which is doing there's a lot of flow going on because it's aerodynamic. So you've got a lot of interchange across the
sparse matrices.
Your grids. Yeah. A lot of interactions that you have to manage.
By the way, in a very competitive field like automotive, Formula One, your model of the occasional high demand workload. Within that field, is that something where the competitive aspect is so intense that staying in the cloud might make a lot more sense because AWS and Azure and Google constantly bring in the latest and newest technologies, the most powerful stuff. Whereas if you're relying on your on-prem with, say, a 3 to 5 year cycle, you might fall behind.
That's more of a case I've seen with GPUs, where like once a GPU is a year or two out of date, most people don't want to use it anymore because the pace of development's been so high. So people are amortizing GPU investments over 2 years maybe, and that means that it's actually more cost effective to use them in the cloud in many cases. So if you can amortize something over 5 years, then the cost goes down a lot more. So it's something to do with the pace of development. Formula One's a bit different. This is the Formula One organization that sets the rules, which is the project I was talking about. They weren't limited from a funding point of view, but the individual teams have cost caps and they're only allowed so many hours of simulation and things like that. They're very constrained. Otherwise, the high budget teams would just run away and trash everything. They'd have so much more budget. So they're trying to get the teams to be more competitive by having cost caps, and the access to compute and wind tunnel is managed across the 10 teams that are in Formula One, so they all have to compete on a more level playing field.
Yeah.
It's less of an issue. But it does mean that one of the sort of proposals that's been kicking around is to just give them a cloud resource. Like, okay, you were going to give you this resource and it's provided in the cloud, and we take it away when you've used up your resource. And we'll just check that you're not cheating around the edge somewhere, right?
You're allocated X amount of time.
But that's not, I would say that's a fairly specialized thing. If you're doing weather forecasting or something like that, you've got a predictable thing. You're going to run it every day. You can run 100% utilization every day. You know what you're doing. You know that tomorrow's going to come and you're going to need to do something. So there are some workloads that are relatively flat, and those are well optimized. And also with this climate model, the NCAR model, they were running it on AWS, but running on a data center environment, it ran a little more efficiently on the InfiniBand, and they were looking at the costs and things and saying, if you need a system to be there for a long period of time and you can keep it busy, it's cheaper to have it in a data center still. But the cost of cloud versus data center is gradually moving towards cloud. The cloud is getting higher quality, faster. You can probably get faster processors there. There's a number of things you can get access to sooner. If you've got a 2-year-old HPC environment in a data center versus this year's cloud, you're starting to see additional offsets and things. So the continuous technology refresh is another aspect, certainly. So I think it's getting there, and it depends which workload. And I think what we're seeing over time is more and more of HPC is going to be viable in cloud. It's just going to move gradually that way. And there's certainly you can find workloads that will prove either side of the argument if you want to go pick your data.
Can we ask you, what's the next big thing in cloud HPC over the next, 24 to 48 months?
I can't say anything about what AWS is doing, but what I personally am really fascinated by very large memory systems and CXL and what's happening there. I just saw the CXL 3.0 announcement of it, and the idea that you'd use CXL as a fabric instead of InfiniBand, I think is fascinating, very low latency, coherent protocol, and the ability to build some sort of rack scale memory clusters. The chipsets are going to take a few more years to come. So that's one. And I've been waiting for persistent memory for 20 years and would really like to have some persistent memory one day. What was the Intel one that didn't work out?
Optane.
Optane, yeah. Optane, right. I think you had to use it with an Intel chip, and it was a sort of proprietary interface. And I think whatever replaces Optane should be on CXL. And maybe we just got to wait for somebody to do a non-volatile memory on CXL.
Well, I think Samsung announced something at Hot Chips conference a couple of weeks ago.
Cool.
Our last episode covered Hot Chips. I don't know whether we mentioned it or not, but there are definitely people working on that.
Yeah, when I was at Sun, we used to go to Hot Chips and go off to Stanford, bring all the field technical specialists in and hang out at Hot Chips with the chip designers. It was super fun. That was an awesome event. I got great memories.
It really is, yes.
That's becoming a big time conference.
Next year I'll go. I'll make sure it's on my calendar next year and I can get there again.
Yeah, for sure. Well, speaking of events, I know Adrian is going to be at SC22 as well. So those of you who are interested in continuing the conversation, let me or him know.
Yeah.
All right. Well, great to be with you both. And Adrian, we hope you'll come back and talk with us some more.
Yeah, I'm not going very far, and certainly happy. Plenty more topics. We didn't talk about open source and a whole bunch of other things. And as I get back into HPC more, I'm sure there'll be some more interesting topics to discuss.
All right, excellent. Thanks so much.
Perfect. Take care, guys. Thank you.
Cheers.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The At HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.